Welcome, welcome, welcome. They're playing with turtle graphics and for loops and programming one, so it's starting to get fun for them. So they got questions. Oh, we can draw things. Oh, and now they're all just like, yay! So yeah, they actually are interested more now because it's more fun to make shapes on the screen. So I'm glad I found something that got them excited about it. But anyway, it was funny. I have to tell you this in my first class this morning. I'm showing the turtle graphics, right? And I have a sample program, and we changed to where it looped like 50 times. It did a bunch of loops and changed the angle every time. And it starts drawing this little spiral shape on the screen and this color. And I'm watching some of my students on the screen while it's drawing this spiral. It's getting bigger and bigger. And I got a student going, and she's just staring and got her mouth open like, wow. She thought that was so cool. Like, just so watching her draw all these little spirals around there. So I can't wait to see what she decides to draw for her program because she was just like, "Whoa, cool!" So I'm like, yeah, that'll be fun. So well. So hope you had a good weekend. I made it to the movies this weekend. I went and saw Running Man, which originally was a Stephen King novel, apparently, and then Arnold Schwarzenegger made a movie about it, like 1990 or somewhere back there. And now they've made another movie about it with Glenn Powell, who is in everything. I see him in commercials. I see him in like all these different movies. He's like the it guy right now, I guess. But they made another one, and apparently, from what I've read, this movie follows the book closer than Schwarzenegger's version. And they took a little bit more movie liberties as they do with books. This one apparently follows it, but I liked it. It was really good. My wife liked it. She's the one that picked it, and it was good. We liked it, enjoyed that. But it was a great weekend, absolutely great weekend. I got some things done. Got my dishwasher fixed finally. It's not leaking all over the floor anymore. It actually finishes a cycle. Took it apart, checked all the seals, got everything back together. Yay, it's working. Put up some towel rack for my wife, a couple of different towel racks, fixed things. And then, of course, there was this great football game this weekend. So I had to wear my Hawaiian shirt, my OU Hawaiian shirt today after we beat Alabama on Saturday. But I expect us to beat Alabama. We're like 5-1 against them in the last 25 years. We own Alabama. We can beat them repeatedly. So I enjoyed that a lot. Anyway, well, let's take a look at our curriculum. We're talking about loops as well. What a coincidence. They're learning for loops and turtle graphics. We're playing with loops as well, but we're learning some cooler stuff about loops than what they're learning just the very beginning, just the very basic, for loops. We're going to get into some cooler loop stuff today. So let's go take a look at our grade screen to see what our good stuff is this week. You should have. Oh, I have not turned in my program for iterative loops. You had iterative loops program last week. I did not turn mine in. We're on recursion, 3.03 recursion. We've looked at repetition with iterative loops. Now we're going to look at recursive loops, 3.03. So, yep, I'm behind on my work. Parent-teacher conferences tomorrow night, by the way. If the parents want to come up and see us, we'll be here till 7:45. Recursive functions. How do you eat an elephant? Well, one bite at a time, right? That's the old saying. But the logic is actually pretty sound. That is how you would eat an elephant. To accomplish a large task, you got to break it into smaller parts, or in this case, smaller bites, because you can't really eat a whole elephant in one bite. In Python and other computer programming languages, this is known as recursion, which they define it as the process of solving a problem by breaking it down into smaller and smaller versions of itself. A method of solving a problem that's based on solving small parts of the same problem over and over. Recursion works, now this is pretty cool. Recursion works by a function calling itself. So inside this defined function, it keeps calling itself. And so that's the loop it's in. It runs and then calls itself again and runs and calls itself again. So this process will repeat indefinitely, like an infinite loop, unless it is stopped by some condition, which is important to make sure you stop with some condition. The condition is known as the base case. So we have some vocabulary to learn. The base case. It's a condition in a recursive function that does not make a recursive call. This is the reason why we would not keep calling the same function over and over again. Once the base condition is met, the program will exit the recursion. So let's take a look at how this can help solve a familiar problem, like how to binge watch an entire show, right? So you got this Canadian show on Netflix about this like Korean couple that owns a convenience store with the little girl named Janet. It's a great show, by the way. I forgot the title of it is. It's my favorite streamed show that I've looked at in the last 5 years. I think I'll have to get the name of that. Identify the base case first, so you know when to stop. So you start off thinking, all right, how many episodes does this have? When's the last episode? Okay, it goes 5 seasons and there's 12 episodes a season. So when I get to the 60th episode, season 5, episode 12, that's the last one. Decide how to get there. What does one step look like? This is where the function will call itself. All right, I will start with episode 1, and when it gets to the end, I will go back and call it, just watch the next episode, and just watch the next episode. I'll just keep calling it, watch the next episode, until it's the last episode, and then I'll stop repeating this. So think of it like a journey. Break it down to one step, like one episode plus the rest of the journey, the rest episodes. Like I'm not going to try to put 6 TVs at a time and watch 6 episodes at the same time. I'm going to watch one episode and keep repeating this function. So then act recursively. After we go through the first episode, check to see, is there another episode? Is this the last one? Nope, there is another episode. So go back to step 1 and let's watch the episode. Keep calling us up. This watch the episode. Is this the last one? Nope. Okay, let's watch the next episode. Let's watch that episode. When we finally get to that last one, stop checking for more episodes. This is the base case. Oh, this is season 5, episode 12. This is the one I've been looking for. I will not repeat after this. We have a programmer spotlight this week. Oh, Atari and Activision. Atari is like one of the original game systems that you could buy for your house. Carol Shaw. She's the first female game developer. As a teenager, Carol Shaw dominated at all the interscholastic math competitions because math and computing is the same type of logic. Generally, if you're good at one, you can be good at the others because they follow the same thinking process. Thus, why I teach math and computer programming. As a student, she graduated from Berkeley, one of the most elite computer science master's programs. Well, at least at the time. I don't know if it still is, but. And as a highly sought after graduate, she took a job with Atari, becoming the first female video game designer. While at Atari, she created 3D tic-tac-toe. And this is what I think is really, really cool, thinking about it. She had to figure out how to apply artificial intelligence in a game with limited RAM. Because, yeah, the 3D tic-tac-toe, you're basically playing against the computer. You had a single-player mode. So you're playing tic-tac-toe against the computer, which means she had to create an AI for the computer to make its move. Right? Playing tic-tac-toe, it has to decide what's the best move for it to make to try to beat you. And the memory was very, very small. Memory was very, very expensive when Atari came out. I mean, if you get 4 megabytes of RAM, it may cost you $100. 4 megabytes. Today, we buy 4 terabytes or gigabytes. 4 gigabytes is hardly anything today, but 4 megabytes would cost like $100 back then. So these game cartridges had very, very little RAM to work with when you played. And so she had to figure out how to create an AI thinking computer with a very, very little bit of memory space that could play competitively some 3D tic-tac-toe. Pretty cool. That's some real talent. Later, she designed games for Activision, which was a company that came shortly after Atari, where she created River Raid. It was an immediate hit, won several awards. But despite her success, she's quite humble, and she's known for saying, hey, I just got paid to play games. Hey, man, that's a life right there, getting paid to do what you love. She liked to play games, and that's what her career was, and she just got paid to play games. Fun stuff. All right, page 2. That's the bottom of that page. Iteration versus recursion. So we talked about iteration last week. It's an age-old debate. What's better, the book or the movie? Well, I didn't read the book. I went to the movie. But before we start an argument, let's all agree that both books and movies exist to serve a similar function, to entertain you with a story. The same is true for both recursive and iterative functions. They both repeatedly execute a set of instructions, right? but they go about it in different ways. And sometimes it makes more sense to use one over the other. Now, I don't know if there's ever a situation where one would work and the other wouldn't even work. I don't think that's the case, but there may be certain cases where this would be better than that. So recursion calls itself to repeat a block of code. It's a function that calls itself. It keeps calling its same function. The function will call itself until it reaches the base case, which terminates it and stops calling itself. It must include a termination condition. Well, all loops need a termination condition. Iteration, loops to repeat a block of code. This applies to loops. Will repeat an executed set of instructions until a certain condition is reached. Like a while loop, while x is not equal to no. Must include a starting condition and an execution statement that updates the control variable. Right, that got to change. If it never can change to no, your while loop will run forever. So how do iterative and recursive functions compare in Python? So both programs below will count the number of chapters in a book until it's finished. The one does it with recursion and the other with iteration. So let's look at this. Here's a defined function. It's called read chapter. It has one argument, n. All right, so in this function, if n equals 7, then print, congratulations, you finished the book. Otherwise, if it's not 7, print the chapter number you're reading. And look, it calls itself. Go to read chapter n plus 1. Well, read chapter is the function that we're running. So when the program starts, we define the read chapter, we define the main. The first thing we do is we run the main function. In the main function, only one thing happens. It calls the other function, read chapter. And we send the number 1 because we're going to start with the first chapter. So in the main function, it calls this. So then the program goes up here and says, okay, here's the function, read chapter, and 1 is the argument that was sent. That doesn't equal 7. So it's going to go to the else, print chapter 1, we print the 1, and then it's going to add 1 and call itself again. Okay, we read chapter 1. We go up here and say 2. Well, that's not the end. Print read chapter 2, 3, and it'll keep repeating, calling itself until n gets to 7. Then it knows we're done, and it will go back down to the main function, and there's no code left, so that's the end of the program. So let's copy this. Oop. Open up our idle window. Okay, there's read chapters. There's that first function. There's the main function. Run. 1, 2, 3, 4, 5, 6. Up. N equals 7. It exited now after it printed this. Congratulations, you finished the book. So there must be 6 chapters. When it gets to 7, no, there isn't a 7. You're done. And it's done. So that's how it works with this recursion, where we create a function and the function keeps calling itself until it meets a certain condition. Now, with the iterative define main, we don't have a separate function. Maybe we'll copy and put this over here. We don't use a separate function. It's just written in part of our main function. Chapter equals 1. While the chapter is less than a 7, print the chapter you're reading, and then add 1. Go back to the loop again. Oh, still less than 7. Add 1. And look, you can add 1 by doing plus equals. Plus equals 1. And look, the output's exactly the same. When I hit run program, nothing changed. So this is a way to do that. You know, we could also do it chapters equal chapters plus 1. That's the exact same thing, but it's a shorter, easier thing to do plus equals. But either way, this works just as well, whichever way you prefer. The other uses less memory because it's a plus equals. But that is the comparison between recursion and iterative. Maybe times when this would be a better way to do it. Other times, maybe you can just put it in here. So recursion is best used to solve a large problem that's easily broken down into smaller and smaller versions of itself. Right? Like if we're doing several different books, right? Read chapter 1. Maybe this is the first book. And then you got another book, read chapter 1. And maybe you got 5 books and you just keep calling it and sending it through this loop. Where over here, we would probably have to repeat this 5 times, once for every book, unless we put this inside of a loop inside of a loop. So there may be times where it's better to have recursion. To produce code that looks cleaner and often shorter, that would be cleaner, just to put the different books down here and keep calling that same function. When the amount of memory is not a concern, right? Because this, we keep doing this, a loop inside a loop. This might not be, this is not as much lines of code. It's only 9 lines of code, where this was 13, including the empty spaces. So, but if memory is not an issue, you can do the recursion. Iteration is best used to complete a task by just repeating the steps until it's done, to the loop. When code needs to be easy and to read and follow. Yeah, because this we have to jump from down here back up to here and keep jumping back up. But this is just a loop. We just keep going through the same loop. It's easier to follow. When you have limited memory or limited time, this may be better as well. But both of them work. They both have the exact same output. It doesn't really matter which one to achieve what you want. Maybe a preference thing. Recursion and iteration self-check. All right, we got a quiz here, ladies. We're going to drag and drop these sortable items into either recursion, iteration, or both. So I'm going to open up the chat. You can just put an R, an I, or a B if you want. You don't have to type the whole word. But which ones use a repetition statement? Does recursion use a repetition statement? Does iteration use a repetition statement? Or do they both use a repetition statement? What do you think? R, I, or B? R, I, or B? Recursion, iteration, or both? Deegan says, I think iteration would use the recursion, the repetition statement. Like while something equals this, or for loop or something. Great job. That is correct. How about it terminates when a base case is recognized? There's a base case. Is it the recursion that will terminate the iteration, or both? Recursion. Yeah, this word was first introduced in this lesson. We just talked about base case as our new vocabulary word, and recursion. That is a recursion process right there. Terminates when a loop condition fails. Terminates when a loop condition fails. Believe that's a recursion. Believe it's an iteration. Oh, maybe it's both then. Since one of you said one, once a day, let's try both. Nope, it's not both. It's not recursion. It is iteration. It is iteration. Yeah. Oh, yeah, you guys went to iteration. Yeah, because the iteration uses the loop, where the recursion uses a function. Right. So yeah, it is terminates when loop condition fails. Produces simpler versions of a problem. Is that recursion or iteration, or both? Recursion. Yeah, absolutely. Modifies a counter, which eventually makes a loop condition fail. Something's counting. Think it's iteration? It is, absolutely. Because again, that uses the loop, where this is a repeating function. Involves a termination test. It tests to see, do I terminate? Yeah, both should do that, right? Because these are both types of loops. And if we don't have a termination test in both, we're going to get an infinite loop and be in problem. Uses the loop statement such as for or while, a while loop, a for loop, some kind of loop. Yeah, that we said iterations loops. Uses repeated function calls. Calls the function over and over again. Iteration was the loop. Recursion used the function where it kept calling itself. Which one can occur infinitely? I guess if we don't get to that termination test, yeah, either one could occur infinitely if we We make a mistake. We don't want it to happen infinitely. Which one involves repetition? Yeah, that's definitely both. Uses a selection statement such as if else. If this is true, else do this. Recursion. There you go. Well done. You've successfully identified the similarities and differences. All right. So yeah, they're similar in a lot of ways. It's just the method they use for their loop repeating is just a little different. All right, page 4. Drawing with a recursive function. We're going to play a little turtle graphics ourselves here today. Have you ever seen a snowflake? Well, you live in Northwest Arkansas. You've probably seen a snowflake. When you look closely at the different parts, you may notice something interesting. The tiny parts of a snowflake look like snowflakes too. These shapes are called fractals. A fractal is a pattern that produces a picture which contains an infinite amount of copies of itself. If you have the same shape over and over and over again, you keep putting them together to make bigger shapes. It's just a fractal that fits into itself. And there are university professors that spend their entire career studying fractals. I met one and saw some major fractals. The whole floor of this room was fractals that they built. You don't need artistic skill to draw fractals using Python. You need recursion. You need to repeat in Turtle Graphics. To experiment with fractals using Turtle Graphics and an idle, you got to use this Turtle Graphics idle. So it might be good to note where this is because this idle does not have Turtle Graphics. We have to use a different Turtle Graphics idle. But give it a shot in this Python get activity. So yeah, if you open this one has Turtle Graphics built into it, where our other idle does not. So 3.03 has a Turtle Graphics link. So let's look at Turtle Graphics fractals. Import the turtle. My turtle equals turtle.turtle. We have a function. Create spiral with 2 arguments, my turtle and line length. I would assume line length, len is length. If the length is greater than 0, I want you to move the turtle forward that length and then turn right 90 degrees. And then call itself. Look, that's the function we just called, create spiral. Call myself, but this time send the name of my turtle and subtract 5 from the line length. So I want you to go back to the same function that I'm in, but subtract 5. Is the line length still greater than 0? Yes. Then let's move forward, turn right, and then call myself again, subtracting 5 more. Is it still greater than 0? Yes. And it'll keep doing that until it's no longer greater than 0. Then it'll exit. So in our main function, we're just calling this function up here and tell it to start with a line length of 100. My turtle, which is what we named our turtle up here before the functions, use my turtle with a line length of 100, and it'll keep going through here until it's no longer greater than 0.
Okay, very good.
Oh, it's drawing it down. I gotta move down here. So the line length is 5 less each time, and it'll keep doing that until it's less than 0. 0 or less. It's no longer greater than 0. So there it is. It drew this recursive function spiral. This function kept calling itself until finally the length was no longer greater than 0. So that's kind of cool. It was easy to change. If we just say, let's start with 200, we can just send a new starting value and just run the function again. Oh, it's going off my screen at first. It just keeps subtracting 5 every time. Now it'll run more loops, but it'll still stop when it gets to the same no longer greater than 0. Just using the same function repeatedly until it hits that base case where, I don't have a line to draw anymore because it's no longer greater than 0. Oh, that's kind of fun. Different way to do it instead of using for loops. Turtle Graphics, import turtle. Define tree, branch, length, and T. T is our turtle. See, we named our turtle T in the main function. Tells it to use the turtle screen. My win equals turtle screen. Left 90 degrees. Pick your pen up. Move backwards 100. Put your pen back down. Grab your green marker and call the function. The function's called tree. Send it a length of 75 and use the turtle T. So here's the tree function. We sent it 75. Yeah, 75 was our starting length. So if the branch length's greater than 5, then I want you to run this whole thing right here, which means it'll move forward like the first time, 75. And it's going to turn right 20 degrees. And it's going to then call itself again, tree, with a branch length that's smaller. So it's going to be 60. And it'll come and says, okay, I'm going to draw it again. So now I'm going to draw another 60, move right 20 degrees, and call myself again, subtract it down to 45. It's still greater than 5. So it's going to draw 45. This is going to draw 30. This is going to draw 15. Then finally, this is not going to be that big anymore. And then it'll draw the left portion of the tree at some point here. Let's see what this looks like. So we're going 20 degrees, so 75, 20 degrees, 60, 45, 30, 15. And then when it got to the end of that, it stopped calling itself and now come back and with this left base. And then it got to the end of there and it came back and drew a shorter one and then another one and then came back and drew the left one. So it keeps backing up a little bit until it runs out less than 0 and it has to back up to the next branch. And when it finishes all the way to the right, then it comes back and draws one to the left. That's the end. It backs up again, goes to the right, then draws a left, and then backs up because it ran out all the way to the right, to the left, backs up to the right, to the left. Kind of an interesting thing it does there. So every time it gets to the end on the right, it comes back and goes to the end on the left, back to the last branch it took off of. There's a lot to that. It goes backwards every time to the last length, whatever the last length it was that sent it there, and calling itself multiple times inside there with shorter branch lengths. So, okay, until finally it gets to 0, right? So when it gets to 0, then it turns left 40 degrees. You know, if it's 0, backs up, it backs up and keeps drawing until it runs out. Slide 3. Read the code, try to predict the output. Modify the thickness of the branches so that the branch length gets smaller as the line gets thinner. So we want thicker branches on bottom, thinner branches on top. Run program. So let's see. Branch length, if it's greater than 5, go forward, turn right 20 degrees, subtract the 15. This looks like it's the same. Left 40, go right 20 degrees again. Till it keeps getting, till the branch length gets down to 0, then it'll back up and draw the next branch. This looks the same, calls 25T. Okay, I think it's the same thing. If we run this, it looks like, yeah, it's doing the same thing. We just have to figure out how to modify the thickness of the branches. So as the branch length gets smaller, the line gets thinner. All right. So we need some thoughts on that. So that would have to do with the line thickness. Let's look up our reference to see that we're using the proper command for the thickness of the branch. Turtle graphics, number of steps, radius, circle, color, number of steps, hide turtle, left angle, pin down. Pin size, that's what we need, the pin size. We want it to be a wider size towards the bottom of the tree. And as it gets thinner, we want it to be, so it's terry.pin size.10. So let's see. So we need probably at the bottom to start with. I'm going to just paste what I had, but it's not Terry, it's just T. That's a pin size of 10. What is that? Is that a good thickness? Okay, that's a good thickness for the beginning ones. But we just have to figure out, if we start out with a pin size of 10, how do we make it smaller as it gets up to smaller branches? Okay, pin size 10, left 90 up, backwards 100, down 10. So it goes up to this tree. And as it goes forward, we want it to get smaller. So it goes up 20 degrees, turns, then we make a recursive call with a smaller branch length. Okay, that's shorter every time. When it gets to the end, it gets shorter every time. So we also want it to get smaller every time. So let's see. After it turns right 20 degrees, was it pin size? I think that's the command we use, right? Yeah, pin size. How do we want to do that? We're going to need to send another argument up here. But let's just call it S for pin size. So let's do that then. Let's call this S and just define S. S equals 10. So our pin size is 10. But we need to send that same pin size up here so it knows that we're dealing with pin size. So this be pin size, I don't know, S minus 3 or something. Well, you think that'll do it? If we make the smaller after it turns right, bring the pin size down 3. This we're going to have to call S as well. And then maybe after it turns left 40, T dot pin size S minus 6 or something. I'm just guessing here. Haven't played a whole lot with the changing the sizes. T dot pin size S minus 9. Just trying it to see if this is going to work. Now, most of Turtle Graphics is for me. So every time after it turns right or left or wherever, I'm taking the pin size down 3, 6, and 9. Oh, S, not X. Let's just see what that does. Kind of. The left ones are smaller. Some of them are smaller. We've definitely got some smaller branches up high, but we've also got some that kind of stayed the same thickness. So I'm going to call that a partial success. But I'm not sure when it went left. When it went left, it's going smaller. Left is going smaller.
All right, last question.
Maybe we need this before it turns right 20. Well, I don't know though, because left 90 up, backwards 100, and green. Well, when it first moves forward though, would be the right there. What would happen if we put this before the first time it moves forward? Let's put it up here and see. Run program. No, it's still making the same size on the right every time. Now we don't have it coming down at all. So we do need it back here. Try to run it again. No, we don't want this up here. Apparently that doesn't do it.
All right, make sure to see you guys. Get those turned in. Others that are not there, exit it.
Well, we have it every time it goes left. I'm not sure on how we would make it after that first turn to the right. We're not getting a smaller size right here in this T forward branch length. I don't know. Well, maybe play with that. If you figure out that solution on how to get it to work everywhere, let me know, because it is smaller. Hello, future Mr. Brock here. I was just looking back at what past Mr. Brock was showing, and I figured that out. That was driving me crazy. Let's take a look at this. Okay, if we have the code right here, and this is the program that we were just looking at there that has the tree branches on there, we can go up here and modify the code the very first line after the if branch length is greater than 5.
Can I swing by there today?
If we go in here and we put P dot pin size branch length divided by 10 right here. So what the branch length is as it goes through each time, we'll just divide it by 10, and then we run that. Watch what happens. Here we go. Run program. There it is. The higher the branch, the smaller it is. So the thickest is definitely at the bottom on that. So that addition to the code allows us to achieve what we're trying to do. If we make it divided by 5, it can show even a difference that's a little more drastic even. See, it's starts with a much thicker trunk, and they're still thinner as they go up. But if we divide by 5, it puts it as a larger starting trunk. But that was it. Mystery solved. I'll let you get back to former Mr. Brock there. Well, thanks, future Mr. Brock. Man, I was making that way too hard, wasn't I? Isn't that usually the case in programming? All right, let's get back to it. Kind of cool. Fractals in film. Animators and special effect artists use fractals to create stunning visuals in movies. In Guardians of the Galaxy Volume 2, the interior of Ego's home is huge and seemingly endless, because he's supposed to be like a god or something, right? This effect was created using fractal mathematics. In Star Wars Episode 3, fractal techniques were used to generate the lava flow during the final lightsaber battle. And in Frozen, fractal patterns appear and surround Queen Elsa as she sings Let It Go, and all these crystals appear in the air, right? Lots of good stuff there. Fractals are used a lot. All right, that is the end of the lesson. We have 5 questions. What's the base case of a recursion? What's the disadvantage of programs that use recursion? Select the conditional statement that will not result in iteration. So, what's the base case here? Select the base case that applies. So, all right. Got some fun stuff to play with there. I kind of like that little tree branch thing. Got to dig into that and figure it out a little bit more. Figuring out other people's code. Exactly how did they do that? And again, we had partial success from making the branches smaller as they got up. So something good to play with. So, all right, that is it for. We just have the 5-question quiz this week. Then we've got a week off for Thanksgiving. Whoop whoop whoop. Go see some family or something. Get together. Get caught up on some sleep. Get some Netflix binge or whatever you plan on doing for the week. Eat too much, whatever's on your agenda there. Hope you enjoy yourself, and if I don't see you Wednesday, I'll see you sometime next week after the holidays. We only got 2 weeks plus finals when we get back, so there's 3 weeks altogether when we get back. 2 weeks of regular stuff and then finals week.